Welcome to class number 24. In this class we will see how a switch loop occurs and how STP spanning tree protocol helps to detect the switch loop. So in this topology we have three switches, switch 1, 2 and 3 all connected together, and there are two PCs, PC2 and PC3. So PC2 and PC3 are in the same network. So when PC2 tries to ping PC3, it needs to know the MAC address of PC3. For that, it will send a ARP request who has 10003. So the ARP request is a broadcast type of communication because this needs to be reached to all the devices in the network. So the destination MAC address of ARP request is all Fs. So once this packet comes to the switch 2, this frame, switch 2 will send it towards Ethernet 1 and Ethernet 2. Because it's a broadcast, switch 2 will make a copy and send one copy towards Ethernet 1, another copy on Ethernet 2, because except the received port it needs to send it to other ports. Okay, so let's examine what will happen to these ARP requests when they are going out from the switch 2. So blue one is going towards the switch 1, yellow one is going towards switch 3. So let's see what happens to the blue one. So the blue ARP request, when it reaches the Ethernet 1, switch 1 will look at the destination MAC address and identifies that it is a ARP request broadcast. So it needs to send it on all other ports except the received one. So in this topology, it will send it towards from Ethernet 3. So once it receives on switch 3 also will do the same thing except the received port. It will send it this way and this way. So the PC2 ARP request has reached PC3. So this is good. But here this copy of ARP request again went back to switch 2. Now what switch 2 will do? Except the received port, it will send it this way and this way. So now the blue one, if you see, it goes in the circles and it will generate multiple copies of the same ARP request, and eventually within minutes there will be like so many ARP requests going through these links, saturating the links, and also switches CPU will be handling all this ARP request forwarding. The similar thing happens with the initial yellow one. So this yellow ARP request will go to the switch 3, and what switch 3 will do, it will send it this way and this way. And switch 1 will do the same thing, it will send it this way. Yeah, so then switch 2 also received the yellow ARP request back. So now once it receives on this port, it will do the same thing, it will send this way and this way. So as you can see, the yellow ARP request also going in circles and making multiple copies, and eventually the links will be flooded with all these ARP requests, and switches will be switches CPU will be like taking care of like forwarding this. So eventually switches CPU will go high and links also will be saturated with all these ARP requests. So within minutes, this particular topology, what will happen is all the links will be flooded with ARP request and they will be saturated, and there will be like no enough bandwidth for the actual traffic. On the switches side, they will be flooded with all the ARP request so that the CPUs will go high and eventually switches will die. So this whole topology will go down if there is no spanning tree. So what spanning tree will do is it will automatically detect the loops and will disable one of the link. So once we disable one of the links, there will be like no ARP request going in the loop. So let's see how spanning tree will detect the loops and block one of the port. So each switch when it is running spanning tree protocol, it will generate BPDUs, bridge protocol data units. So the information in the BPDUs is the bridge ID of that switch. So bridge ID is has two components. One is priority and address. Address is a MAC address of that switch, and priority is a value. So the default value will be on the Arista switches is 32768. So as you can see, switch 1 will send this information to all other switches in this network. Same switch 2 and switch 3 will send its own bridge ID details, so that all the switches in this network will be able to receive the information about the bridge IDs of all other switches. Once they have received that information, they will elect one switch as a root. So the criteria to select the root is whoever has the lowest bridge ID. So bridge ID is a combination of priority and MAC address. So if the priority of all the switches is same, then MAC address will be the tiebreaker. So let's see the bridge ID details. So priority is same for switch 1, switch 2 and switch 3. So let's look at the MAC address. First two is 0C, 0C, 0C. So far it's common. Let's look at the third one. Here it is 2, here it is D, here it is B. So as MAC address is hexadecimal format, the priority will be like 0, 1, 2, 3, 9 and then ABCDE. So in this case 2 will be the lowest one. So ideally this should become the root bridge. And what is the next one? D or B? B is the next priority. So this is the first priority because it has the lowest MAC address. Then the next one is this, and the next one is this. So let's see all switches agreed switch 1 as the root or not. So on the switch 1 I am issuing the command shows priority root detail, means we are asking the switch 1 who is the root in this spanning tree or like switch network. So root ID is 32768, and if you see the MAC address 0C 2D because 2 is the lowest one, and this bridge is the root because if you see this is matching. So when we ask the switch 1 who is the root, it is saying that okay, I am the root. And let's ask the same information on switch 2. And switch 2, if you can see root details, who is the root? Whoever has this MAC address 0C2. And how it can reach that root switch? Ethernet 1. So this is the shortest path to reach the switch 1. So next we are asking switch 3 the same details. So it is also saying root is in this switched network 0C2. And how it can reach the root switch? Ethernet 3. Okay. So for now switches exchange the BPDUs and selected switch 1 as the root in this topology. Now let's see the port statuses. So now switch 1 has become the root. Okay. So all the ports on the root will be in the forwarding state in working state. Means root switch, all the ports will be in the forwarding state and nothing will be discarded. So we don't block the loop by discarding one of the ports. So all the ports will be in the forwarding state, so in the working state. And root ports are something, so this switch 2 has like fastest way to reach switch 1. So it has two ways to reach, either it can go this way or this way. So in this topology it's this is the through Ethernet 1, it's the faster path, so it is selected as a root port. So this one will be also in the forwarding state. Same for switch 3. So this link and this link will be active. So next this link should be blocked to avoid the switch loop. So let's see. So out of these three links, these two should be in the forwarding state because on the root side all the ports should be in the forwarding, and all other switches, whatever the best path to the root, they have to be in the forwarding state. So that's why this link and this link in the forwarding state. Now we should block the traffic through this link. So to block the traffic, either switch 2 has to discard its interface or switch 3 has to spanning tree has to discard Ethernet 2 here. So in this way, so as we have seen the MAC address, the bridge ID priorities, this was the first one because it has the lowest MAC address. This was the second one, and this was the third one. So ideally, whoever has the highest MAC address in this topology. So in this link, so this has 0CB, so this is lowest, and this is 0CD, so this is highest. So out of these two, which bridge ID will be prioritized? This one. So it will not block this port instead. So switch to Ethernet 2 will be discarded. So let's see that information. So when you issue the command show spanning tree topology stated, it will show what ports are in forwarding state and what ports are in discarding state. So in switch 1, if you can, as it is the root, all ports in the forwarding state, and switch 3 also in the forwarding state. So we are not blocking anything here. And next, on the switch 2, as in the tiebreaker between the switch 3 and switch 2, it has the highest MAC address, so the port on the Ethernet 2 should be in the discarded state by the spanning tree. As you can see, the output Ethernet 2 discarding means it will not accept any packets on this. So this way spanning tree will identify the switch loop and will block one of the port so that there will be no loop, right? Because if you see it is breaking here, so there is no loop, it's not connected. So let's see what happens to the ARP request. When PC2 sends the ARP request with the destination F, so it will come to the switch 2, and this port is in the blocking state, so there will be no ARP request going this way. So it will only go this way, and this and this. So this one will never be delivered to switch 2 back because this port is in the discarding state. Assignment for this lab is build the same topology and verify the STP station with STP status on each switch, and use these commands and identify which one is root and each switch bridge details and which port is in the discarding state. That's all for this class. Thank you.